we have started our chapter, and now we are close to finishing. And so this was, I was talking about how to prove algebraically 1 1. Okay, so 1 1. Okay, x1 equal to x2. I was taking an example of this. So x square 1 plus 1 is equals to x square 2 plus 1. If I am able to show that from here, if I am able to show that x1 is equal to x2, then it would be 1 1, or else it would be many to 1. Okay, so as I am here, x1 square 1 1 cancel, x1 square equal to x2 square. Okay, so now be careful. If we are multiplying, we are putting remainder both sides, then we would get x1 equals to plus minus x2, or x1 equal to mod x2. Not necessarily mod, we don't need any mod sign, and so a lot of confusion or is created. Okay, so x1 equal to plus minus x2. As we are able to see, in one condition it is x1 equal to plus x2, but if it's the second condition is true, meaning x1 equal to minus x2, then it would not be 1 1. So therefore x square plus 1 is not 1 1. Now you would say, give me an example. So to give you an example, it's minus 13 and 13. Okay, so both here we are applying that function, putting the value of x as minus 13 and 13, we would get 170 only. But so it's not 1 1. But in reality, we are talking in given conditions, it could be possible that it's only natural number, so minus would be rejected, or it's given that whole numbers cannot be negative. So it's possible that minus 13 in given conditions or in acceptable conditions could be rejected, or 13 could also be rejected if we are only taking negative numbers. Okay, so as now we talked about 1 1, algebraically proved. Now we second need the onto one. Now what is onto? Onto, now we have to prove onto. Onto now can be easily proven. Okay, onto. Onto and range are mainly same. As in onto conditions, range is equal to codomain. Okay, main the concept how we prove was range is equal to codomain, and by that we would prove that range how to prove, like if the function is, if there is the equation of the function is given, then we would be able to prove that the function is onto or not. Okay, so as we were talking, we have taken an example, fx equal to x square plus 1. Okay, so as we are talking about this example, can we write y equal, okay, starting with normal, same equation I am writing, fx equal to x square plus 1. It's very simple, fx equal to x square plus 1. The first thing I am starting. Okay, it's the same, fx equal to x square plus 1. Okay, now can we write fx as y? Yes, we can write y as x square plus 1. Okay, this equation will be given in the question. I am just taking from that example. Okay, this will be given in the equation will be given in the question. Okay, so y equal to x square plus 1. Now to prove that this is onto. Okay, to prove that we need x in terms of y. So can we write y minus 1, bringing 1 to LHS. Then y minus 1 as x square, and then we get x as root under y minus 1. This is the value that we are getting. So if you are seeing this equation, then is that true that for every value of y, for every value of y, for every value of y is there an existing x? Yes, for every value of y there is an existing x. Okay, so like I will give an example 1, then x would be 0. Then if I take an example 10, then x would be 3, plus minus 3. Okay, so there exists one or more x's. That does not matter. But for every value of y, there should exist at least one x, value of x. That should satisfy that equation. That is how to prove onto. And one more we can prove is this was algebraically. Now I can prove it graphically. Graphically meaning that sometimes there is no equation given and we are on graphs. So how to prove that? Okay, so it can be a very complex graph. So I am taking the complex graph as y equal to sine theta. Okay, y equal to sine theta makes this graph as this. Oh, y equal to sine theta. Y equal to sine theta. Okay, so as we are able to see this graph, now we would perform the horizontal line test. The word is horizontal line test. Okay, so now this word only suggests horizontal. Horizontal meaning the vertical lines, horizontal lines that is straight up to like this. And we would draw many horizontal lines. Okay, so we would draw many lines like this. And these are vertical lines. And these vertical lines, and that would be exactly parallel to, it should be exactly parallel to the y-axis. Y-axis, I should name it y, and this is y dash, it's x dash, and it's x. Okay, so if we are drawing many vertical lines, to clear this graph, as we would not be able to understand this graph in complexity. Okay, so this is the graph, x, x dash, y, y dash. And this is the equation, and like sin x starts from 0 and like it's a continuous graph, and here you can name it 2 pi, it's pi here. Okay, so this is a graph of y equal to sin x. And if you can think in our mind, or you can make these horizontal lines. Okay, so if you are making horizontal lines in this here in this graph, what you would see simply is that there is no horizontal line possible. There is no if there is a condition that there is no horizontal line possible that would attach 2 points of this curve of this straight line. Okay, that's not possible. This curve, no horizontal line parallel to y-axis can touch this curve. I have taken an example y equal to sin x. Okay, if this is not possible, then it is simply, we can say it's onto. Simply we can say it's onto and nothing else. It's onto directly, you can say. The given function is onto. Okay, so by here we proved that how we can prove that the given function is onto or not. Now moving further. Okay, so this was graphically methods to prove that a function is onto or not. And now there is not only one type of function, like I was given example sin theta. It could be x square plus 1. It could be log x. It could be ex. It could be many types of x. Y equal to if it's y equal to fx, then that function could be many types. Okay, so now we would start with types of functions. So in types of functions, we should know that it's somewhat power functions. Power functions meaning like x square, y equal to x square, y equal to x cube, y equal to x4, y equal to x. Okay, and logarithm function, y equal to log x, y equal to log 2x. Okay, now I will make these graphs. Okay, so if it's power function y equal to x, we know this. Y equal to x square would go like this, and it would be more and going like this. Okay, and this would be y equal to x square, x cube, and like this it would go on. That is power function. Exponential function. Now the second topic comes is exponential logarithm functions. Okay, so here as we are able to see, we can prove that this is logarithmic, this is exponential functions. These two L's. Okay, this is L and it's these two L, it's logarithmic and it's exponential. Exponential meaning y equal to ex, y equal to 2e2x, y equal to e3x, y equal to e4x, okay, going on. Okay, and we should know one thing, y equal to e raised to the power x into e raised to the power 2x would give us the e raised to the power 3x. Okay, so this was the main concept of functions, and now moving further, we should now Now we have studied many types of functions, but are functions over here? No. Now it's binary operations. We can name it to some separate thing from functions. It's very much separate from functions. As about just binary operate. We should binarily operate that function. Okay, so binary operations. Okay, so binary operations, if I write A star B, then that if is given as AB. It's given. If this equation is given that A star B is equal to AB, then it's simply, yes, then it's will be a binary operation. Binary operation can as function, it could be addition, subtraction, multiplication, division. Okay, so that's binary operation. And now how can we define that what is binary operation? We can say that binary operations is a set of numbers that could be replaced by an arbitrary. What is the spelling of arbitrary? You should know that spelling, and the spelling of arbitrary is ARBITRARY. This is the spelling of arbitrary, and arbitrary set X. Okay, arbitrary set X, and that's only the definition of binary operations. So I can repeat that definition. We can simply say the set of numbers which has to be replaced by that arbitrary set X. It's normally set X, and by any binary operation, subtraction, addition, multiplication, division is nothing but association of that pair of elements, and that's binary operation. Okay, so that's binary operation, and it could be from real number to real number, from irrational number to irrational number, from rational number to rational number. It could be anything to anything, and it should be forbidden with the given condition. If it is a real number, we cannot take the examples of complex numbers. If it is given to natural numbers, we cannot take the examples of rational and irrational or real numbers. Okay, so if it is given natural numbers, we can take all natural numbers and not irrational numbers and complex numbers. Okay, so by this, okay, so this was the main concept of binary operations. Binary operations gives us a separate topic, as it in functions what we did was there were two sets. One in binary operations there is an arbitrary set X. Okay, arbitrary set X. Then only it would be binary operations, and therefore we have. And thank you, congratulations, we have completed our chapter. Bye here.